Thanks for coming, everyone. So my name is Voloch. I work at Palantir, and I'll tell you guys about model compression. Sure, you can go to the next slide. Cool. So here is sort of like a recurring story that happens if you want to keep like sort of like simple models. So chapter one is that you have some data, and after you clean it and featureize it, you go and someone tells you, okay, go build a model. Next. And then you go and you build a simple model that has, let's say, an AUC of 0.65, and then you tune the hell out of it, and then you pull all kinds of tricks, and then you get an AUC of 0.7. Next. Yeah, and then your boss turns to you and he says, okay, I did not hire you to build me shit models. Next. And then you go, oh, but if I build a more complex model, then it's going to be really hard to maintain it because the users might not be as technical, and it's hard to debug, and it's hard to interpret. And there's like all kinds of problems, but still it's problematic. Next. And your boss turns to you and he says, okay, nice pairs of glasses you have there. It would be a real shame if something happened to them. And chapter 8 is you go and you finally build a more complex model, and after doing all kinds of things, you might get an AUC of 0.8. And the issue is that like forever you're going to live with this complicated model, which is hard to interpret and hard to debug, and there's all kinds of issues. And the whole point that I want to show here is that like this implication does not have to hold. So just because you tried a simple model and you got like shitty metrics, and then you tried a complicated one and you got good metrics, it does not mean that you need to live with a complicated model forever. Next. Cool. One more. Cool. So that's the concept of model compression, is that from a complicated model that has like really good accuracy, you can somehow like map it down to like a simpler model while preserving like a lot of the accuracy that it has. And why would you do it? Like, it's easier to maintain, it's easier to debug when you have problems with your data. It's faster, it requires less memory and energy if you're using it like in mobile or in like cars or something like that. And very importantly also, it's easier to interpret. That just makes it like much easier for everything. And so yeah, this concept like shows like, for example, like in this paper, if you guys want to read more, and as well as some others, but that's a good starting point. So I'll show you guys like a pet example of how this can work. So the first thing that we do there is that we have your training set, and you build a decision tree to like with that model, and you get an AUC of 0.77. And then you go and you build a random forest, and after tuning and doing all kinds of things, you can get an AUC of 0.85. And now you are at that stage that you think you might be stuck with a random forest forever, and like you're never going to be able to visualize the thing properly and so on. And next, yeah. So the following like trick is an example of like of model compression, is that you can train decision tree using the labels as predicted by the random forest. So as you guys can see here, instead of using Y-train, for example, you can use the predictions of the random forest as the labels for that. So you're pretty much ignoring the real labels, and you're just using the labels as the predictions of the more complicated model. And very often the claim is that this really boosts the performance, and like I don't know, there is this gap of like 8 AUC points, and depending on your particular needs, these like 3 AUC points might be fine for you to live with, and you might prefer to use a decision tree, for example. And the intuition behind this is that like obviously like real data has all kinds of issues with it. It has outliers, it has mistakes, it has all kinds of things. And when you train this like more complex model and you use those predictions, it kind of like smooths out like the surface that you're trying to train on. And in that sense, it makes it like easier for like a simpler model to feed that data. And cool. So that's the sort of like the most basic example of how to do this, and there is like all kinds of other tricks that you can do. One, and this is always very hard for me to say, hierarchically train incrementally less complex models. And so by that I mean like you can try like random forests with like stronger and stronger regularization parameters, or like less trees, until you like sort of like go down to a decision tree, for example. If you have a lot of unlabeled data, for example, you can use your complex model to label that data. And yeah, you can basically have like as much unlabeled data as you have, and then train your simple model with this like huge previously unlabeled data set. And that works out well as well. And the third part, which is really like well explained in that paper, is that you can also like synthetically generate data. So for that, like I'll defer the details to the paper, but you basically create a lot of fake data and then label it with the complex model, and then train the simpler one based on that. Cool. So the summary is the following: is that you have model compression is useful in making complex models into simpler ones, which can make like life much easier. And just to clarify, this doesn't apply only to random forests and decision trees. It's like a general sort of like pattern. And it's pretty easy to do, like in its simpler stages. You just have to train a simpler model with the labels coming from the more complex one. And as we mentioned, like if you have a lot of unlabeled data, or if you don't have any more data to train on, you can synthetically generate data, as described in that paper. And yeah, and analogous concepts that we didn't talk about exist for like for deep learning models as well. But the idea there is a little bit different. In the sense, it's mostly about like reducing like the space required by the model for like energy consumption, for example. And yeah, that's all I have. I think I have time for one question only. Yeah, so there's a few different ways. Like one is that you can just look at the marginal distribution of each of the features, and then like generate each row where each column is like independently generated according to that marginal distribution. So that's like the base example, and in the paper they describe ways to approximate the joint distribution and generate like something which is not independent. But that's the basic idea essentially. Yeah, it's a good question. So I use the regressor because I trained on the predicted probabilities. So the labels were like numbers between 0 and 1s rather than just like 0, 1. Let's see it. Cool. I will take more questions like during the break if you guys have. I'll go for the next speaker.
I'm going to talk about my research on distributing taxis across a city. I'll start with a description of what VIA does. We're building what we think is the future operating system for transportation that is a shared on-demand service. Can you go to the next slide, please? So that's a screenshot of our dashboard. Each pin is a taxi, and they're going across the city, picking up and dropping down passengers. Can you go to the next one? Each blue person is an origin of a booking, and each orange person is a destination. In order to avoid detour for passengers already on board, we ask riders to go to a nearby street corner as indicated by the small lines. This allows very large sharing, aggregating multiple rides into the same vehicle, which is both ecological and allows us to offer shirut taxi level prices with a special taxi feeling to the service. Can you go to the next slide? So here's an example of our online algorithm that matches rides that have similar aspects into the same vehicle. In my talk, I am not going to talk about this matching algorithm. It deserves its own talk. I'm going to talk about another problem we have, how to instruct our drivers to start their workday. When each driver starts working, we send them a path to a specific location to be at. Why is this? Two reasons. One, we want drivers to be close to where there will be bookings. We'd like our customers to have 3 minutes wait time for a taxi rather than, let's say, 11 minutes. Everyone knows this, like if you're using a taxi and so on. And another thing is we don't want to pay drivers too much for their dead time, whether it is when they're parking or on the way to their first customer. Next. What we usually do for this is look at where the bookings are early in the morning and produce some kind of heat map across the city. This is data from the taxi authority in Singapore. We have similar data for our real service. And we have an algorithm that matches taxis according to this information. I'm going to talk about what we do when this approach doesn't work. Why might it not work? When we're spreading into a new city, next slide please. There are unique challenges that are related to the small scale of the service. There's a small number of early adopters, and we want to give them very good service so that we'll have good word of mouth and will grow. But we don't want to spend a lot of money paying drivers to drive taxis to be able to pick all these passengers up. It's possible to use a few vehicles because there's only a few bookings initially. It's hard to use statistical methods because noise overwhelms the signal when the numbers are small, and the big issue is that we can't spread our vehicle supply as thinly as we like. If one neighborhood has demand justifying half a taxi and another neighborhood has demand justifying another half a taxi, we have to pick one. Okay, so I'll get into the details of the problem for new cities. Can you go on? So we'd like our drivers to cover as large an area as possible. But we can't tell them to stop just anywhere. For example, it will be very useful to have a driver on Ayalon because they can get very quickly to a large area from there, but we can't tell them to wait there for a ride. So our local teams mark places that are safe and legal to stop across the city, and we send only those places for our drivers when they're starting their shifts. We have a known number of vehicles that are available for our service. Once our service has been running for a few days, we have information where our demand is, and we can run the shareability algorithm and see which rides will be shared when they're run through the system. And the output we want to produce is how many taxis to send to each location out of the list of locations. In order to minimize the total passenger wait time, this is equivalent to minimizing the average wait time because it only differs by a factor. And it's not, the goal function won't have a driver dead time at all, because since we pay for a driver's time anyway, the only cost to us of a driver parking and waiting for the first ride is the opportunity cost of the better service they could have offered if they'd been elsewhere at the time. So how do we formulate this mathematically? Next slide. We define these variables. The X variables are the outputs that you want, how many taxis to send to each location across the city. And, well, okay, leave it at that for a minute. And the Y variables are or indicator variables that indicate the entire scenario of which ride would have been picked up in the scenario we're looking for, and we're going to optimize over both X and Y at the same time. For each ride, there are multiple Y variables. Almost all of them are 0, and one of them is 1, indicating where we send a taxi for this specific rider. And this binary information encodes the entire service early in the morning. Our goal is to minimize the total wait time that would have been in this scenario, this expression is a sum over all locations and rides. Most of the terms in the sum are because almost all the y's are 0. For each ride, there will be one of these variables will be 1, which indicates which van would have picked this rider. And we just insert a numerical constant of how long it would have taken to drive from this stop location to the rider's booking point. This allows us to, this is a very simple expression because it's just a linear expression in the variables. We have similar constraints on the problem. Click please. Which are of similar form. They're all of linear forms. The total number of taxis we allocate to all of the location is the total fleet size. Every ride is served, every booking should be served, and the number of taxis we send out of each safe to stop location can't be more than we send there initially in the morning. So this class of optimization problem where all the where the target function as well as all the constraints are linear functions of the problem variables is called a linear program. You may remember this from your CS classes. Can you go to the next slide, please? These problems are easy to solve when the variables are allowed to, or real numbers are allowed to vary continuously. However, once you have discrete variables, integers or booleans in our case, they become exponentially harder. Solvers takes a time that is essentially exponential in the number of discrete variables and doesn't depend on the number of continuous variables. In our case, the x's, we have a few dozens of them are integers, and the y's, we have a few thousands of them because it's a tensor product of locations and bookings. They are binary. This is thousands of integer variables, which is totally impractical to solve. However, we found out, so what do? We pored over algorithm textbooks and papers and found out a neat trick. Once the x variables are set to concrete values, the problem of optimizing for just the y variables has a special form. It's called a totally unimodular linear program. These kind of linear programs have the property that the solution, even if the variables are allowed to vary continuously, the solution will always be in integers. I won't get into what this technical condition is. It's on the coefficients on the problem. In our case, it allows us to say that the x variables must be integers, and then the y variables can, we relax the condition and allow them to vary continuously to have whatever value they want between 0 and 1. But we're guaranteed by total modularity of the partial problem that the optimal solution will have all y variables either 0 or 1 in the best solution. So if we set the x variables to be integers and y variables to be continuous, this will be, the problem will be tractable. It's solved practically within seconds because we have only a dozens of x variables corresponding to safe locations in the city. The solution will be the same as before. Y's will be, the optimal values for y will be Boolean numbers. So this made us pretty happy. And another thing we can do now is, is that we can vary the constraint on the total number of taxis and see what marginal gains we get from adding another taxi to the service and see if it's worth the cost or not. So a word about how we did this research. We used the, can you go to the next slide? We used the Python library PulP. It's a library for linear programming. And it's has very straightforward interface. You just variables. Here we set the x's to variables that are integers and y to general variables, and we give the objective in almost exactly the same form, as close as possible to mathematical notation within Python, which made it very easy to experiment and tweak our approach and find out a solution that basically worked eventually to find the best possible distribution we can. So this is it. Any questions?
Basically, what does library grant to the programmer that and like right away. So like you have the formula, right? Like you know which place is taking the most rights request, and you know where to actually put, you know, where to send the driver because he has parking or not. So you have the mathematical formula what this library brings to the problem.
Right, so what do we benefit from using this library? You need a strong solver. So, solving the problem with a dozen integer variables is not something you can program by yourself. You need to use an optimization library, and they're usually written either in Fortran or, if you're lucky, in C++, and you need to wrap them in Python or construct text files with inputs that they'll parse and run for you, which is very unwieldy. This library, because it's so easy to use and uses strong solvers in the backend, made it very easy to experiment from different representations of the problem until we found this one that had the property that it can run fast. Yeah. Okay. Thanks, everyone. No problem.
So JamBot is a project that I did with Yal Gross, who is over here, and Yossi Adi, who is not, and who's turning the slide? Okay, so what's JamBot? Essentially, it's a program that should help unskilled, inspiring musicians that have no idea how to play to be able to play music. So we wanted to create such a program that helped them, but since none of us, maybe except Yossi, have any formal musical education, we didn't want the program to have any either. So in order to do that, we wanted the program to be able to listen to music and to understand what's important, and for this we need some kind of supervised data. So there's actually a lot of other programs that generates music and all this, but they usually use boring public domain MIDI data sets that it's like very old songs and it's not very fun. So we used a program called Guitar Pro. Guitar Pro is a program from sometimes around 2005 that is mainly used for kids to learn how to play guitar, and it contains a lot of rock pop songs that we can use. And in order to demonstrate to the program what it's like to play with unskilled musicians, we treated bassists as unskilled musicians, obviously. So we created a bunch of guitar and bass pairs, and trying to learn how the guitarist responds to the playing of the bass. So this is what a guitar profiles looks like. You can see there's a bunch of tracks: lead guitar, rhythm guitar, bass, and percussion. And for each timestamps, you can see what the instrument did at the timestamp. So this is the guitar strings, and this is when you play the first fret on the E, then press nothing on the A string, and so on. So we couldn't use such a thing. We wanted to use a smaller domain because we didn't want to learn the entire scale of the guitar. So we limited both the bass and the guitar to a single octave. And we used BIO tags to model whether a note is played or not. So, and we had a lot of problems representing the time, and we ended up just using absolute timing. Next slide. So this is an example of what the data looks like. This is apparently should represent the bass and the guitar of Hazy Shade of Winter by Simon and Garfunkel. You can see for each timestamp, we have 12 notes, and B means we pressed on a note, and I means we didn't release the note. So you can see the guitar kind of plays more notes than the bass. For each note of the bass, there's roughly 2 notes from the guitar. As you can see, like this is a single note, and this is 2 notes from the guitar. So, okay, so I have a demo of what a parsed song sounds like, because it's kind of messes things up. So this is like the ideal output of the system. So this is something from the data side. Okay, so, and we wanted to learn from it. So the model we use is kind of a standard LSTM model where we treated each 12 characters word we seen as a word, added it to 12-dimension vectors, feed it to an LSTM, and then try to predict the guitar part for this timestamp. In order to do real-time playing, we connected a MIDI keyboard, parsed it to the 12-character format, used the model for prediction, turned it back to MIDI, and then sent it to logic. So, next slide. So we have a bunch of demos. First, we feed it the bass of Blitzkrieg Bop from the Ramones, and this is what came out. Can anyone recognize it? In the end, it stops playing, you can hear the bass. So. This is just the bass. Okay. So this is the output of, and the other example is actually me playing with it. So I manually added an effect for my playing, so it could be distinguished from the JamBot playing. So it sounds kind of funny. That's it. And so there's a lot of future work that we need to do, because currently there is no normal way to evaluate this thing, and there's a lot of metadata we didn't use, and we expected a lot of things from the model. For example, we didn't specify a genre when it trained it, so it's just learned all the genres. It doesn't distinguish between lead guitar and rhythm guitars, which have totally different rules when they play. So that's why it's kind of a mess. And that's about it. Thank you.
Hello, I'm Monica Sue. I'm from Intuit. I'm a data scientist there. I'm actually from our California office, but I'm here working with our Israeli team as well. And I'm going to tell you a story today about one of the problems that we're working on. It's called Battling Adaptive Adversaries. It's a story about fraud detection and prevention within one of our products, which is called TurboTax. And so I'll start by giving some context about TurboTax itself. And the reason for that is so that you can understand the type of fraud we're detecting, and also because the problem that this product is trying to solve is somewhat specific to the United States and Canada. So you might be aware that in the United States, virtually everyone has to file manually an annual tax return. And there's actually a deadline. It's usually April 15th where everyone has to do this. And it's quite a painful process because you should also be aware that the United States tax code is quite complex. So if you were to do this manually yourself, you would be filling out many, many forms across hours and perhaps days. And the last point, which is also really important context, is that around 77% of filers receive a refund check, so money back from the government after filing their taxes. And that's because as you're paying your income tax throughout the year, you can overpay, and ultimately the government will pay you back. The reason that's important context is because there's money involved, and that's why this is an attractive area to fraudsters. You can do the next one. And so to it, just as a brief introduction, along with what Bat already mentioned, we have a suite of products which aim to simplify the finances of both consumers and small businesses. And next one. And TurboTax is one of our products, and it serves to simplify this tax filing process for United States and Canadian customers. Next one. Next. So this problem of fraudsters trying to take advantage of this tax refund, the source of that problem is that there's been a growing number of data loss incidences within the public and financial sector. And so I won't go through all of these statistics, but I think it will be no surprise to anyone that there's a growing number of personally identifying information that's available to fraudsters who'd like to take advantage of probably a lot of systems, including tax ID theft. And the last point is, Intuit is not battling tax ID theft on its own. We actually are working with the IRS, the Internal Revenue Service of the United States government, as well as other industry players and the State Department of Revenues. So this is an article that was published about this problem. And the reason this is an interesting problem from a data science perspective is that fraudsters are constantly evolving to evade our detection strategies. So we have to build better models and get better along with them. And we use a multifaceted approach to detect fraud. And I'm going to tell you about one of them, which is very heavily data-driven. And I'll go through some lessons that we've learned along the way. So one of the really important lessons is that we need to centralize all of the data across our products in order to get a really holistic view of fraud in our system. So ultimately, we're trying to distinguish legitimate customers from fraudsters, and you need to collect all of the data that you possibly can in order to do that really, really well. So this includes application logs, such as the login data from everyone that's trying to log into TurboTax. It includes clickstream data, so tracking all of the clicks within our products and how people are interacting with the website and mobile app. User entered data, so that is, of course, what they're actually entering in their account, as well as the tax filing itself. And we also use some third-party data, so we get signals from external to Intuit to help solve this problem. Really importantly, we centralize all of these data sources in a Hadoop data lake, and this is what allows us to build models utilizing all of these data sources. So on top of the data lake, actually, if you can go back. On top of the data lake, we have this, actually, if you go back one, an analytical layer. And so this is where we build models and perform analytics to better understand fraud that's suspicious activity in our systems. And then on top of that, we also importantly have an operational layer. This is where the forensic analysts can actually comb through the data, identify suspicious activity, and do something about it if unfortunately something happens in our systems. Next one. So the first lesson was to centralize all the data. The second lesson is to have a continuous feedback loop between that operational layer and the analytical layer. So as I said, there's forensic analysts working in the operational layer, and they're identifying suspicious activity, and they're sending labels to the data scientists and analysts who work in this analytical layer. This is the most powerful part of our infrastructure because we're continuously injecting human knowledge and expertise into the models that we build. So labels allow us to, of course, build supervised machine learning algorithms or models, but it also allows us to validate unsupervised machine learning. And then in return, we send them actually, go back one. In return, we send them our risk scores that come out of our models. And this is really important as well because we can seed their investigations and we can validate the results that we get in our current models. Okay. So if we look more closely in the analytical layer, this is an overly simplified picture of how we build different components that are reusable for different data sets and use cases in our systems. So a featureizer are building features to use in supervised machine learning, and we do this in two different ways. One is in a continuous fashion using Scala Spark and MLlib to have continuous data featureization for close to real-time featureization for predictive modeling. We also have a batch pipeline which uses SQL and Python in order to have another set of models, but not acting in real time as the data comes into our data lake. The other components are more of a platform, so they're reusable for different data sets and use cases. We train and test models. We publish our signals that are used in our models to an external key value store. And of course, we have metrics and monitoring as well. And the last is to actually not just detect fraud within that analytical layer, but bring those insights back to our products so that we can prevent fraud in real time. So again, this is an overly simplified picture, but we want to enable our products to make real-time decisions about how to act on suspicious activity. So we do that by servicing our models to a model host, and at every login event in TurboTax, the product is able to retrieve a risk score and therefore move from detection to actual fraud prevention. I want to go through an example of a supervised model design. So I told you we have a continuous featureization as well as a batch featureization. And in one example of our batch featureization, we use a random forest classifier. So this is something you probably are very familiar with. We have a decision tree here, and at each node you're making decisions about whether something meets a certain criteria at every node, and ultimately you're deciding whether something is good, a good customer, versus a fraudulent actor. And random forest is a collection of decision trees. We like it because they can be trained in parallel. They're fast to train, test, and validate, and you can get feature importance for free, so you can learn about which features are actually important for detecting fraud. The reason I'm mentioning this is because we've I guess, had a challenge of running scikit-learn, where we build our decision trees over MapReduce, because our models are quite complex, or they're quite large, and we wanted to parallelize them. And we use the Hadoop streaming API to do this. And so to train the model, you can train each tree with a separate mapper, and ultimately write one file into HDFS, into Hadoop, per tree. And then in the reduce step, you're combining all of the trees into one model. And similarly, there's a separate MapReduce step to ultimately make a prediction. And the last thing I want to mention is that we heavily utilize Luigi in our pipeline. So this batch pipeline, I said, is a combination of SQL and Python, SQL to do the featureization, and Python to do machine learning. And the SQL part is hundreds and hundreds of SQL scripts. And it's a pain to actually manage all of the tasks that are required, because there's a ton of dependency on one another. So we use Luigi, which is a dependency manager for tax execution. And as you probably know, it's written in Python and was built by and open sourced by Spotify. It's a really nice task manager, because you basically create a class for each feature or for each task that you need to run in your pipeline. You specify the command, the command that actually runs that script, and you can specify which tasks need to be run before that can be run. And this has been super critical for managing our hundreds and hundreds of SQL scripts required for this pipeline. So in summary, the lessons that we've learned from fraud detection at Intuit is to first centralize all of our data sources, and we do that in the Hadoop data lake. We set up a feedback loop between operations and analytics. This gives us continuous labeled data and human intelligence injected into our models. We perform continuous data processing for some close to real-time detection. And then we actually move from detection to prevention by enabling real-time decisioning in product. And that's it. I can take questions. Yes?
Yeah, just out of all of that, I can see how it would help make a faster feedback loop. But how did you actually do cases where you had the first one cases, people adapting to the features and realizing that your models weren't working on them? Or cases when you make an example?
Yeah, that's a great question. So we do have a feedback loop, but sometimes those labels get stale because they're evolving. So you kind of can, pardon me? Oh, I'm sorry. He asked how, I don't know exactly the words that you used, but basically as we have this feedback loop set up between the operations people and the data scientists, how do you make sure your models are able to evolve to the latest activities that the fraudsters are doing? Is that correct?
More like I was actually asking, how do you adapt when there's someone who's adversarial in this case? Not just updating the model, that you would do anyway. I think how do you specifically adapt to somebody recognizing that, I don't know, whereas people with X amount of apartments are more likely to commit fraud or not likely. How do you adapt to somebody acting on that?
So as the fraudsters are changing, some of our labels will get stale, and the newest labels might have these new patterns, like the ones that you just described. And so what we do is build models that are just based on the most recent labeled data, in addition to one that have different look-back windows. Does that make sense?
Maybe I missed it, but why do you use Scikit and not Spark MLib on your classifier?
So we have two separate fraud detection pipelines, and one uses Scala Spark and MLlib. But the one that I was talking about is more of a batch pipeline, which we're using both SQL and Python. So we do use it. Okay, thank you very much.
I'm kind of skipping the details of what are decorators, what is aspect-oriented programming, and just skipping to the gist of 5 useful decorators. Hopefully, at least one of them would be useful for you. Okay, so let's start. So, just a second. A decorator is basically what comes after the @ sign before a function. So you can see a sample decorator here. Now, one very useful decorator is called the least recently used decorator. All you have to do is you add the @LRU cache and the amount of cache you want, and your function can perform better. Now let's see how that happens. For example, I have this classic example of the Fibonacci function, implemented rather naively. As you would expect, the Fibonacci of n is the Fibonacci of n minus 1 plus n minus 2. And I time it. So I time it for Fibonacci of 30. And it runs for approximately 440 milliseconds. Now, by using this simple decorator of keep the last used entries, return values, forever, no maximal size, the function runs for less than 1 millisecond. So 126 nanoseconds. So that's all I changed, like typing like 10 characters. So you might say that, okay, Fibonacci is kind of a made-up example. Give me something that has something to do with data science. So those of you who work with natural language processing are probably familiar with the Levenshtein distance. A Levenshtein distance is basically between 2 words, the amount of insertions and deletions that you have to make. For example, assuming that I have the word reshape, and I want to measure the distance to the word shapes, I remove the R and the E and add an S at the end. So the Levenshtein distance is 3. Okay, so very simple definition, and it's very, very useful for autocorrecting spelling mistakes and search. So this is how you calculate the Levenshtein distance. It's a recursive function. It's even optimized here. It's not clear how you might make it run faster. And now we run it on real data. For those of you who aren't familiar with, this is a really cool trick. All Linux machines, including Mac, have a dictionary. So what I did here is I randomized 10 words, 10 real words from the dictionary. And this is what came out. And I calculated the Levenshtein distance of all possible combinations. So 10 times 10, it's running the function for 100 times. Okay? And I measured the performance of this Levenshtein distance once with the LRU cache, the memoization, and once without. So let's see the results. Okay, so look at this difference. I have here, with the memoization, it runs for approximately 10 milliseconds, and without 40,000 milliseconds. I'm not demonstrating it here because I have limited time. You can see that with a simple insertion, everything runs faster, and I didn't have to implement anything on my own. Okay, so memoization is nice. Memoization is actually caching in memory, but memory is limited, and most of the time I want to cache on my hard drive. So let's see how we can implement this caching with Decorators. Okay, so what you see here is a pretty simple decorator I came up with for writing the results in a JSON format to disk. Now, what this decorator does is basically it gets a function, it stores its return value. If a file with that name exists, it pulls it out of the file. If not, it saves it to the file and returns the value. The use is pretty easy. Let's see, for example. So what I got here is a calculation of 1 plus 1, and I artificially made it to run for 2 seconds. And I won't run it now, but trust me that the first time it would run for 2 seconds, and the second time it would run immediately. Now, this is nice, but what I actually want is to use the parameters in some way. I don't want to save the data in cached.json. I want it to be like Fibonacci of n.json. I want to have the arguments in. Now, this isn't trivial how this can be done. So, introducing the inspection model. Those of you who aren't familiar with, I'll give a short intro. In Python, there are 3 ways to call a function, and 3 basic ways. One is to use named parameters. For example, this function sums 3 numbers and have the third argument optional. Very simple, it gets A, B, and C and sums them. The second option is to get positional arguments and use the star args. Again, the same functionality, different signature. And the third way is to use named arguments using a key value dictionary. Again, with the double star notations. This shouldn't be new to anyone, just Python syntactic sugar. But when I wrap my function, I don't really care how the person, the programmer, implemented their function. I want just to pass the arguments on. So how can this be done? Introducing the inspect model. So the inspect model gives me an option to extract the signature out and to bind my own arguments, regardless of how they're being represented. After binding the arguments, the return value is basically a dictionary, and I can pass them on to my function as a dictionary. So This is how my decorator looks now, using the inspection model. And I passed it on to the default format function that every string has. Now I can call my function with, as we've seen earlier, can you scroll up a bit? Up. The other up. Okay, like this. So the curly braces with the arguments are being replaced by the format function. Nothing on my part, just getting the arguments and forwarding to the format function. Very easy to use, very simple. The code is attached in the GitHub at the end of the lecture. Okay, moving on. A little bit, that's it. Okay, so another thing that the inspect model gives us is an ability to read the function code. Now you might want to ask yourself, why would I want to do this? So a really cool trick I found out. With how many of you are familiar with the Paramico module? Great, good work. So the Paramico module is basically an SSH client written in Python. What this decorator does is basically, it wraps a function, opens a terminal, types in the terminal the code of the function that it wraps, and returns the results back. So let's see how that works. So this is an instance of an SSH client. I call it my server. These are my credentials, very secret. And I have here a local call. This local function returns the current working dir. Very simple, host.get current working dir. If I wrap that function with @myServer, it runs @myServer. And you can see that the return value is different. Here, it's my local drive, my local path on my Mac machine, and this is the path on the remote host. Okay, so we'll stop here because of time limitations, and I'll take questions.
So basically this decorator and my server just performs the same function in the remote,
Okay, so the question was, is the decorator just performing the same functionality on the remote host? And the answer is yes, with a short asterisk. It basically types the code on the remote server. So if you are missing packages or anything else, then it might break.
It's just performing, imagine how I look at it, which is performing Python-C and the quotations and all the functions, right? And just print it and then get the value and return it.
Okay, so the question is it the same as the piping py-.c on the remote host? And pretty much, there's a little bit of pickling down the way to support pandas and other features, but pretty much, yeah. Okay, time out.